Hi, everyone. I'm Brian Schmidt with Geothermal Rising. Welcome to this full steam ahead webcast. Our topic today is Thermal Energy Networks, or TENS, and we have a fantastic selection of presenters to lead this discussion. Before getting to that, though, I'd just like to thank some of our member companies. First up is our Earth Energy Visionaries. This is our highest membership tier. So thank you, Baker Hughes, Calpine, Ever, Exceed, SLB, and Turboden for all your support. We also want to thank our Geothermal Champion members. We wouldn't be able to do these webcasts without member support, so thank you all for helping make this happen. Give you a quick overview of where we're going here. We're going to start off with Isabel Varela from HEET. She's going to introduce the subject and give a recap of some panels and success stories from the recent symposium that we had. Then we're going to move on to Joshua Soble. He's going to give us more of an on-the-ground perspective of TENS projects, specifically focused on the Framingham, Massachusetts project, and we'll touch on France and UK projects as well if there's time. Then Jay Egg will come on and talk about public-private partnerships, technology integration, emerging markets and trends, and sort of opportunities and implications on the larger scale there. Then we will have a Q&A session at the end. Feel free to enter your questions at any point using the Zoom UI Q&A function. We have a few upcoming events I wanted to mention. We have Capitol Hill Day in Washington, D.C. in May. We have an investor forum in June in Houston. We're going to be hosting a geothermal hub at the Image in August, also in Houston. Another geothermal hub will be hosted at RE Plus, which is September in Las Vegas. And we have our joint symposium with SPE which is also in September in Calgary. So without any further ado, I'm going to stop sharing my screen and hand things off to Isabel.
Thank you, Brian. I'm going to share my screen now. Can you see my screen okay?
Looks great.
Perfect. So thank you for inviting me to share the summary of the session, the symposium. So the Thermal Energy Network Symposium was hosted here in the Cambridge area on February 6 to 8. HEET was one of the co-hosts, and we're happy to share a little bit of the summary of the day. It's very difficult to share a summary of the entire symposium. So rather, I'm going to share some highlights of the different panels and sessions. So a little bit about the opening session. There was a session about costs, and that was very lively, and of course, a lot of examples from Framingham. We will share a little bit about the research consortium that HEET leads and that was presented at this symposium. There was a discussion on taxonomy for these thermal energy networks, and also about the ambient temperature loop. So I will go ahead and start. So the first opening was by Zainab Magawi from HEET, and she talked about potential for thermal energy and how currently people don't generally think about the thermal opportunity, especially, for example, with climate change. Our bodies of waters, oceans, lakes, rivers have really absorbed a lot of the heat that can be used by these thermal energy networks. And by using heat from these sources, then we would also help restore these bodies of water, or help at least partially restore these bodies of water to temperatures below what it was, so pre-industrial times. Here in the Boston area, for example, we know that there's, if the bodies of water get warmer, then the ecosystem is affected, and for example, our lobsters are not happy and they move northward. So it would be a way, as Zeynep presented it, to make the lobsters happy and basically help restore our ecosystem while using these thermal energy. Mentioning also that using thermal energy from these bodies of water is actually a very cost-efficient way to get thermal energy. And in this first panel, there was Nikki Bruno from Eversource, Cindy DeMichel from Celsius, and Zeynep Magawi from HEET, talking about the collaboration, the great collaboration that they have in the Framingham project here in Massachusetts. So the Framingham project is the first utility-led geothermal energy network in an existing neighborhood. It is right now operational. It started operations last summer. And there was a session about costs presented by Eric Bosworth on the cost of the Framingham project in the first loop. This is the breakdown that he presented for building conversions, about 33%, the bore field, 26%. Those are the main sources of cost. And then the pump house and civil work and mains and services. The session about costs is always of a lot of interest, especially focusing on how can these costs be reduced. And there is a second loop to the Framingham project, and I know Josh Soble will discuss more about that later, but what Eric Bosworth presented is that the costs are expected to come down by about 40% from the first loop. So the Framingham loop, the original loop is shown here in red, in this red outline, and there is the plan for this second loop that is immediately to the left, and that is also in collaboration with HEET and Eversource and the city of Framingham. And then this is the expansion or the second loop, how budget would look like there, as presented by Eric from Eversource. I would mention here that HEET has a grant from the Department of Energy that was awarded in December for the construction of the second loop, together with the partners I mentioned, and we're hoping that goes forward later this year. In the conversation about costs, Buro Happold presented this curve for the Thermal Energy Network's cost curve, showing that it's really kind of this discrete steps where each of these sections, would be a reduction in each one of these sections as we have more of these systems developed. So generally, we think of, for example, the geothermal networks here in Massachusetts in 3 stages. The demonstration projects that are happening right now, for example, the Framingham one from Eversource, the National Grid has one in Franklin Field and Lowell. So these would be the demonstration projects. And then there would be that development phase where the number of projects increases. And then there would be really that deployment stage. So the cost curve will be different in each one of these, lowering as you have more of these systems being constructed and operational. And then there was a session where I shared about a research consortium on geothermal energy networks that HEET leads. So many people in this audience are familiar with the work of HEET, but often I find that they're not familiar that HEET leads this research consortium that is focused entirely on geothermal networks. And for this, we have collaborators from national labs like LBNL and NREL, and from different universities like Boston University, Berkeley University, UMass Lowell. And each one of the research institutions focuses on a different aspect of these geothermal energy networks. I will highlight here that there is a day where all of these researchers will share the results of their studies. And this is coming up on April 28th. And there's the link for the registration and agenda. This research consortium focuses on studies related to not only the reducing emissions, but on impacts on the electric grid, on costs, on ecology, the impacts of these networks on ecology, on health, and on equity. Presented also at the symposium was this presentation from NREL. Guangdong Zhu presented work by Juliette Simpson. And what they developed is a techno-economic model that they call heat nets. And this model has two parts. One is the engineering part. It's a simulation, a tool that simulates the behavior of the geothermal energy networks, and also estimates costs for these systems. This work is part also of the research consortium that I just presented, and it's work by NREL. These are slides from Guangdong Zhu from NREL showing the different components of the model that they developed. So the reduced order model, or the engineering model, takes into account the different components of the system. For example, how many boreholes, all the system specifications, and simulates how the system performs. So they can estimate the temperature, for example, in the main loop, as you add buildings to the model, as you add more boreholes to the system. And then they also calculate, it's a techno-economic model where you can calculate the levelized cost of the energy, NPV, and the price of the heating or cooling. This is an open source tool that is written in Python, and they will be making that available. So it's meant to be an accessible tool for modeling these thermal energy networks. There was also a session that was that had a lot of attention on taxonomy or terminology about these systems. This is a growing field, and there's been a lot of different names used for these systems. So this is a chart here of generational district nomenclatures for using the 3G district heating and cooling systems, or fourth generation district heating and cooling systems, or 5th generation. And you can see that mainly at the 5th generation, we've come to ambient temperatures. So one of the terminologies that has been proposed is that if these systems use boreholes, if they're decentralized, if they have the single pipe, and if they use at least have, at least one borehole, then they can be called, these thermal energy networks. So this is an ongoing conversation, and there was a session at the symposium discussing this. There was also a session where there was a lot of discussion about the ambient temperature loops and the benefits, the modeling of these loops, and comparing if you have, one loop versus one main pipe versus two pipes and four pipes. So this is just to give you a flavor of the things that were discussed in this symposium, and I'll pass it now to Josh.
Hi, everyone. Thanks very much. I'll go ahead and share my screen here. Is that coming through?
Looks
Very
good.
good. Thank you. Hi again, everyone. My name is Josh Soble. I'm the Director of Business Development for Celsius Energy here in the US. And as Isabel mentioned, I'm going to speak about the Eversource Framingham Utility Thermal Energy Network project that Celsius Energy worked on over the last few years here. First, just a quick background on Celsius Energy. We are a corporate venture of a much larger firm called SLB, formerly known as Schlumberger. SLB is one of the world's largest energy technology firms. We are in about 120 countries with annual revenue a little over $30 billion. The company has been around for about 100 years and specializes in all things in the subsurface. The company's history is predominantly in hydrocarbons, and Celsius Energy stems directly from that centuries worth of experience, technology, expertise, and technology leadership that SLB has in the market, and we're bringing that into the clean energy space, specifically in the shallow geothermal heating and cooling arena. So everything that Celsius Energy is doing is really focused on technology and innovation in the area. Our headquarters is based in Paris, France. We have offices in the UK, the US, and several other countries. I will just be speaking to our work in the Northeast US this morning, but happy to connect with others about our broader experience around the world. And maybe we'll touch on another project or two at the end here. As I mentioned, we're going to talk about the Framingham U10 project. This is about an hour outside of Boston, give or take. The project is owned and developed by Eversource Energy. So the idea here is that there are 3 bore fields on this project that are distributed throughout this neighborhood. These 3 bore fields are then connected to an ambient loop that is roughly a mile long and connects to about 37 different buildings in the neighborhood, delivering heating and cooling to about 140 discrete existing utility customers that Eversource has. Now, what is unique about this project is that Celsius Energy was able to call on some of our innovative bore field design expertise and experience to really enable and facilitate this project. So, a typical geothermal bore field is what we see on the left of this slide here, a standard bore field. You have vertical bores, usually spaced about 20 feet apart from one another. This is sort of the industry standard. This is what anyone who has seen a geothermal project before might recognize. This is what has conventionally been done in the space. One of the major drawbacks to this, of course, is that you need a large area of land in order to install a bore field of meaningful size on a given project site. And there's going to be a lot of disruption on that project site when you are constructing the system and drilling all of those bores into the earth. So Celsius Energy has a proprietary system that's a little bit different. It allows us to co-locate all of the bores at a single point at the surface, and then use incline drilling to have all of those bores fan out underground. So rather than having to tear up an entire swath of land, like what we see in the lower left corner of the slide here in that picture, we really only need a very small surface footprint, that center picture at the bottom of the slide here, from which we can place all of our bores on a single bore field at the surface when we are drilling. This not only shrinks the construction footprint during drilling operations, but it allows us convenient access to those bores after construction once the system goes into operation. So how did this impact the Framingham Thermal Energy Network project? So as I mentioned before, this project consisted of 3 bore fields spread throughout the neighborhood. Originally, all 3 bore fields were designed using a conventional vertical bore field approach. These bores were all spaced 20 foot on center from one another, and all of the bores were expected to be perfectly vertical. Now, the largest bore field, which is on the northern end of this site plan here, that's the top bore field, consisted of 60 bores and took up the entirety of a parking lot that was being used by Mass Bay Community College, which is the structure that you see immediately to the west of that parking lot, highlighted in pink here. In order to install that bore field, that vertical design bore field, the entire parking lot would have to be closed, shut down, and torn up for that system to be drilled and installed. This was a real non-starter for Mass Bay Community College. They told Eversource Energy, you can't shut down our entire parking lot. That's a real problem for us. We need our students, our community members, faculty to be able to continue to use that parking lot. So what we were able to do is change that bore field design and use 2 of these incline pyramids that I previously described. So rather than having 60 vertical bores spread throughout this whole parking lot, we reduced that surface footprint down to just a few parking spaces of footprint size at the surface, where we had these 2 pyramids located in the parking lot. And we reduced the total number of bores from 60 down to 35, and then use this incline drilling technique that we have to have the bore field essentially fan out underground and capture the thermal resource that the original 60 vertical bore solution was going to capture, right? So we have no change in the thermal resource size. We're still getting that same thermal resource, but from a very small footprint at the surface. And what we were able to do was only take up about a quarter, maybe a third of the parking lot during construction operations, and then allow Mass Bay Community College and that community to continue to use that parking lot during construction operations, right? So not only was our construction site just a lot simpler, a lot cleaner, a lot straightforward, but we didn't impact the ongoing business as usual operations of the construction site as much as the project would have. A couple other features to note here. Using this incline drilling, we were able to drill north, south, east, and west out from that parking lot. We have bores going beneath buildings to the east and west, as well as beneath the street to the south. Now, since this was a utility project, it did come with utility right of way. That's how we were able to get permission to drill beneath the street to the south. Typically on most projects, we are not drilling outside of property lines. We're staying within property boundaries. So this was somewhat of a unique project in that we were able to go beyond property lines to install this this bore field. This is just a picture of the second of those two pyramids being installed. As I mentioned before, all of these bores on a single pyramid are being installed from a common point at the surface. So rather than having to move a large drill rig all around a construction site, every time we want to move to a new bore to drill, all we have to do is tilt the mast of the rig for that next bore that is going to get drilled on the pyramid. This construction picture from the Framingham project is from well over a year ago at this point. But during the Geothermal Rising Thermal Energy Network Symposium a few months ago, this past February, we were able to give a tour of the site where we had a 3D model of the entire neighborhood, of the thermal loop in the street, and showing these bores underground, to really give folks a visual understanding of, what does this look like? A lot of times it's hard to visualize what the bore field beneath our feet looks like. So it's great to be able to have this 3D model to show what was going on beneath everyone's feet while we were standing in that parking lot where, just a few months before construction had been taking place. Very briefly, I want to touch on another thermal energy network project that Celsius Energy has worked on, where some of these innovative approaches have had a really profound impact on the project and the opportunity. So in France, we have done a project at the CERN Hadron Large Particle Accelerator. This is a large scientific research center, and the facility creates a substantial amount of waste heat at the facility. Right, so the facility has a lot of different neighborhoods, development zones that are adjacent to the particle accelerator system. And there's one section called Fresnay-Voltaire that has a lot of new construction development and mixed-use development work going on. So there are lots of new construction buildings and existing building retrofit work taking place in the area. And what we were able to do was sort of similar to the Framingham project, in that we have designed both conventional vertical bore fields as well as inclined pyramid bore fields on this project in order to minimize our surface footprint on the project site and minimize the impact that we have to the surrounding area, so that we can install these bore fields on this thermal energy network in a way that will not limit the future development of the neighborhood and of this area. What's especially exciting about this project is that the waste heat that I mentioned before, coming from the research facility, is being captured and actually stored in these bore fields that we are designing and installing in this adjacent neighborhood, so that it can be used as a thermal resource at a later date, right? So, this starts to get into a really interesting conversation around how geothermal bore fields play really well with other technologies, specifically waste heat technologies and concepts, things like that. I know that Jay will speak a little bit more about how geothermal solutions fit into the larger context of thermal energy networks in a little bit. But this approach here, just to make a note of it, this approach of using a hybrid bore field design that calls on both vertical bores and incline bores, has a real impact on the project financials as well, right? So we are able to reduce the total project cost by about 50% while capturing 75% energy savings compared to a conventional HVAC option that these buildings would have otherwise had to use if they did not use a geothermal solution. And the result here was about 5,000 tons of avoided CO2 every year being captured from this project. So this is really exciting. This isn't just happening in the US. This is happening elsewhere. Lessons learned, of course, go both ways. And we're happy to have had the opportunity to share this with the GR community here today, and are looking forward to your questions later in the webinar. I will wrap up there, and Jay, I think I will pass it over to you.
Thank you, Joshua. Thank you so much also for the great work done by HEET. We appreciate everything you do. You've been such an amazing support for the industry. Let me find my share button here and we'll get there. All right, portion of screen, share. All right, so my name is Jay Egg. I'm the president of EggGeo, and I am always privileged to be with these folks that are bringing the industry up to the level I always knew that it would be. Isabel has just been so amazing and such a great addition to the HEET team. Joshua I've known for a little while, and he continues to dazzle me with his knowledge and capabilities, both very highly educated folks in the geothermal industry. And I really want to touch on something Joshua talked about, because recently there was a headline that I saw, and it was a pretty cool way of saying it. It said, the island of Manhattan is being used as a thermal battery because they're planning to pump all the heat from the summer down into the granite underneath the island and store that up for winter. Now, we know in the industry what they're doing is they're going to have a lot of boreholes like what Joshua was just talking about, and that becomes borehole thermal energy storage. Some are under buildings, some are in the road. It's a matter of all of these opportunities to store energy. And when you look at a thermal energy network, it has not only those closed loop bores, which can go just about anywhere. As a matter of fact, one of the things we won't have time to talk about today is they're building them as energy piles oftentimes under buildings, and you'll see some of that as you get further into the built environment and understanding what's going on. And so as we move around a city, a thermal energy network, as you probably know, but I always like to start from the very beginning, is a pipe filled with water that runs in a loop through a particular group of buildings, blocks, or a community. And it has the ability to do what we call thermal advantage or diversified load movement. And so if you have a building like number 9 here might be a data center, or 8 and 9 might be an opportunity to create heat even in the middle of the winter. And where 3 is probably an apartment building, you would be able to pull heat from the exhausted heat from other buildings and use it in the winter time to heat the building. When you end up in the middle of the summer and almost everything is in the cooling mode, that means you're rejecting heat not only from the commercial buildings, not only from the office buildings and apartments and single-family homes and other factories and commercial establishments, but you can put that heat in an awful lot of places. And that's where wastewater energy transfer and surface water energy transfer all come into play, because anywhere that we're moving energy in the built environment is an opportunity to move that heat out of the environment to somewhere that it's either more usable or not really a factor, and can be dissipated by the mass of the earth or the mass of the surface body waters. And wastewater is an excellent place to dump that extra energy in the summertime. It's also an excellent place to gather energy from all these buildings in the wintertime, because no matter what time of the year, it's going to be between 65 and 75 degrees in most urban environments. So some of the things that can use this energy not only are the apartment buildings, but facilities that have swimming pools and surface water for recreation. So this is just kind of a little heat map of all the different systems that can use either as a source or reject heat to the environment. And what's really important in a big overview nationally, just like in this image that the Building Decarbonization Coalition created, it's important to make this understandable to the general public in a very simple and concise way, so that they can see a subway here and exchanging energy with that, wastewater here, and they can see how fields such as Joshua was talking about, such as football and soccer fields, can be used as heat sources and sinks. The surface water, these are always being replenished. They may change in temperature from season to season, but even with freezing temperatures, with a little study, it may be a good heat source even in the middle of the winter, and it's definitely a good heat sink in the middle of the summer. One of the things is important to understand with these systems is, as a group of buildings, most of the time they're cooling dominant. They actually, in balance, they have more heat to get rid of than they need heat. So that means we're cooling dominant. And we're definitely, in the summertime, our biggest challenge is moving heat out of these buildings. In the wintertime, our biggest challenge is moving heat from building to building. Therefore, that's why the energy networks are important. But this isn't all, because it really starts getting blurred when you look at some of the other opportunities, such as they've done over the past few decades at the Cornell campus in Ithaca, New York. So they have always had, since many decades ago, they've had an energy loop, but it has mainly consisted of a heated water loop or a hot water loop and a chilled water loop. And the chilled water loop comes from a central chiller plant, and the heated water loop was coming from boilers and combined heat and power, because they create their own electricity there using natural gas turbines. Well, they've started changing that. One of the first things they did is, instead, and this is geothermal, and this is part of an energy network, so it's important to understand that this can be done. They found that the local surface body, Lake Cayuga, had 40 degrees temperature year-round at the bottom of the lake. So they put in what they called the Cornell Lake Source Cooling Plant. And that cooling plant, simply by running pumps and circulating water, creates almost all of the cooling they need for the campus without even running chillers. That's surface water geothermal exchange at its finest, especially when you consider that for cooling. And then on the other side, instead of doing low temperature heat harvesting from shallow boreholes and so forth, they decided to drill deep wells to see what they could get out of it. So they went down about 10,000 feet, and they're able to get over 200 degrees Fahrenheit water. What they really want is to get hot enough resources that they can actually run turbines and replace this CHP plant, which is burning right now is burning natural gas. And so that's their ultimate goal. So once they do that, they'll not only have all of the heat they need from this deep resource, but without running heat pumps in this case, but they'll also have the electricity they need for much of the campus. Now, if you think about this, while Joshua and Isabel are talking about using heat pumps, that is normally in 99% of the situations the way these systems run in a thermal energy network. However, the purpose of this is to say we don't even need to run a heat pump to cool the campus or to heat the campus in its ultimate evolution. We're using cold geothermal resource here and hot geothermal resource here, because even after they create the electricity, there's plenty of waste heat to still do that. Many different utilities are really in the game. This is a Con Ed example of a thermal energy network, talking about some of the projects that are moving forth in New York. New York was the first state to have enabling legislation that mandated thermal energy networks. I think it's kind of interesting that even though it's mandated in New York, Massachusetts, using Eversource and Celsius and HEET's wonderful input, was able to get the first one in. So Con Ed will be shortly behind them with some of their own thermal energy networks. Another great example of just where this can go is the energy network, the cooling energy network in Ontario. Anytime you can use a hydronic stream, meaning basically a water stream, that's what hydronic means in a pipe. Anytime you can use it for more than one purpose, you are really breaking down silos. And what they did in Ontario in about 2006 is they used this was a public, well, it began as a utility idea, because a company called, I'm going to forget their name right now for just a minute, but their utility company there put in an energy exchange plant that tied in with the water treatment facilities, and they were able to get enough cooling for about, right now they're at about 270,000 tons of cooling. And the way they do that is they bring the water in from Lake Ontario, they run it through exchangers, and they treat it to drinking water standards first, and then in this building, they run it through heat exchangers. And this is another situation where it's 40 degrees year round, which just happens to be the temperature you need for chilled water to remove humidity and to cool buildings. So moving along in the last couple of minutes here, there are European projects. This was created by a European company. This is a project that was completed in 2010 for a downtown district in St. Petersburg, Florida, that included the 911 center, the police station, and a few other buildings. But what's really exciting is we were talking a minute ago about the trouble, and it is a little bit of difficulty to get down this deep to get actual electricity capability from the earth. Well, it's coming close. And with the new administration, as difficult as things may be sometimes, they like the geothermal field. And there's a company called Quaise that is perfecting something in ultra deep drilling using millimeter waves. Basically, it's a microwave oven with focused beams. It gets power from a gyrotron. Have to look that up. But it actually goes down and vaporizes granite or rock. And it vaporizes it to the point where coming up the side, it's just there. It's no longer rock. It's been vaporized. but it turns the sides of the bore into basically a granite glass. And they can go down, they claim, 10 miles. And so if you can get down that deep, because you're not wearing out bits and pulling the bit out every so often, you can get down very deep. Fervo, I'll finish with this. Fervo is perfecting technology that you probably heard a lot about, which is directional boring at a much deeper depth. And the reason for that is they can get more heat transfer area to create steam in fractures in the rock. And our new energy secretary, Chris Wright, is heavily invested in these technologies, which makes it easier for people to understand. So with that, I'm going to go ahead and close up my part of the session just by saying that these thermal energy networks, make no mistake about it, if you think about the natural gas revolution in the 50s and 60s, we ran 2.5 million miles of natural gas pipe to 65 million buildings. That is what we are facing now. The number one infrastructure challenge is the fact that we're doing what they did with the natural gas network with water to move energy around our cities. So this revolution is every bit as profitable for the utilities without any consumptive use or combustion. It's just a better way to do things. And I will go ahead and close it out and stop sharing so that we can let our moderator take it from here.
Great, thanks, Jay. That was fantastic. We do have a few questions that have been submitted here, some of which we've been answering in text on there, but there's some that we can get into live here. Have there been any studies or commercial installations using heat pumps with natural refrigerants to further increase efficiency of thermal energy network heating and cooling? And I will just open that one up to the whole panel here, if anyone's got a.
Two natural refrigerants that are very popular are ammonia, which has a 0 ozone depletion factor, and it's been used for well over a century. The problem with ammonia is it needs to be in a central plant, and it needs to have an operator, kind of like a power plant. But we've used it for ice storage and everything. It's abundant and it's natural. The problem is it's toxic and flammable. The other one is CO2, which they are perfecting it just so fast right now. It makes me wonder why we're dealing with A2Ls, which are the semi-flammable household refrigerants that we see the new phase coming out in. But the natural refrigerant, propane is another natural refrigerant that's been used for centuries. It's very, very safe in the proper applications and also has a 0 ozone depletion factor. That's, for my part, I thought I would jump in with that because I have an HVAC background, probably like Joshua. He's a scientist with a PhD, if I'm not mistaken. So, Joshua, do you have anything more to say?
I was going to say I'm actually a geologist by training.
Oh, there you go. That's right. I knew that. I just forgot.
And I don't think I could top that answer.
Yeah.
I just want to make a related comment, not specifically addressing that question, but related. So for the ambient temperature loop right now, for example, in Framingham, it uses 25% glycol for antifreeze. There are systems in Canada that they use 100% water. Canada, colder weather than kind of the Boston area. So just sharing that about the glycol in the main loop.
And that glycol can be propylene glycol, which we know is food grade. There are companies that have glycerin-based glycols, which have even a better viscosity at cold temperatures. But we're sure trying to stay away from the ethylene and so forth, because that can be contaminant for the ground if it leaks.
Great. The next question I have here is, will these presentations be shared? And I suppose that's up to the three of you on whether you're okay with us sharing these presentations.
You betcha, for me.
We'll see if we can get these sent out to all of the registrants to attend, or sorry, all of the registered attendees. This one, I don't know. We don't have anyone from the DOE on the panel, so I don't know if anyone here is going to be authoritative on answering this one, but I'll throw it out in case someone does have an answer for this. But has the DOE considered putting a national lab on a thermal energy network for demonstration and research innovation purposes?
I don't have an answer to that one, but I can mention something related, and that is that the Department of Energy, through the Geothermal Technologies Office last year, did fund was it 11 or 13 communities nationally to do design phase of these geothermal networks in their communities. From that was last year, and HEET was part of that through the second loop in Framingham, and now they have moved to the second phase, which is funding for the construction phase of these systems, and about 4 or 5 of these communities were selected, and Framingham was one of them through HEET. So that construction phase for these systems through the Geothermal Technologies Office. That's not quite addressing the question, but similar.
That's great to know. Okay, then moving on to the next question. Have isobaric energy recovery devices been trialed at the Eversource site to significantly reduce the cost of pumping water through the network? Recent estimates suggest it could reduce OPEX by approximately 40% for other types of geothermal projects. Josh, I'm guessing that one's aimed at you.
I was actually going to redirect that to Isabel. We have not been doing that, but I don't know if the HEET research team that's been working on the Framingham project with Eversource has done any of that.
So what I can mention is that in general, for pumping through the main loop, so once you get that first fluid going, then the pumping it has that inertia. So the energy cost of pumping is low. It's really the friction around the water on the pipe. So it's relatively low. That constant pumping is all I can mention here. Yeah.
And I have nothing to say about that because we have not been able to make isobaric pumping work in these systems. It's been talked about, but my RPEs kind of chuckle and they go, not yet. That's all. And that may be that we don't know everything. That's why we're out here. We want to hear if somebody has a concept that works for these systems.
Yeah. So the good thing related to this is, for example, some of the tools that NREL is developing, and that can test different things in the system. For example, if you have a bigger diameter of the pipe, what does that do to the COP of the system? Yeah, I don't know if they would be able to address this particular question.
And let's see. What mechanism are you using to calculate the value of thermal energy? Equivalent electricity pricing?
I assume that's a question from the slide that I had on cost savings. Yeah, so that is compared to the existing retail costs of electricity and natural gas at that particular location for the Fernie Voltaire project.
So the next one in here actually looks more like a comment of someone thanking us for the presentation there. We have a question. Hasn't the Trump administration pulled back the money? New Haven, for example, is suing the federal government for their train project, I believe. I don't know if anyone is has an answer for that one. I don't.
We have, I'll just speculate. We've noticed because we're associated with the unions that the new administration is not friendly to unions and training as much as they are friendly to the technology of geothermal in general. So we're still trying to wait for the dust to settle. We just understand we're grateful that they consider it a drilling technology and energy technology, because it could be much worse. Geothermal has not gotten the good end of the deal through other Republican administrations in the past. So we're grateful that it's being accepted along with other drilling technologies as something that seems to be safe. And we say that with our fingers crossed. Once again, I'll say, I just saw a presentation in Syracuse, and it was stated from Donovan Gordon's mouth, who's the director of clean heating and cooling. And I had heard this, but he said that Chris Wright has $100 million of his own money invested into Fervo. And Fervo's a geothermal drilling technology company. And one of the reasons I think this is important, that we are telling all industry players that the lines are being blurred. That was part of the reason that I put up the Cornell slide. The lines are being blurred between low temperature and high temperature geothermal. And with the lines blurred, they can't pull one side of the stick without picking up the other side of the stick. It's that old analogy. When you pick up one side, if we're all one stick, if you pick up one side, you pick up the other. And that is a safe place to be. And in Washington, many people have heard that geothermal is still considered a boring technology. So that makes it bipartisan.
That was good. And we have one more question here. One of the main challenges I've come across regarding thermal networks is the high initial capital cost. How do project developers and municipalities typically address or overcome this barrier? Additionally, I'm curious about the social acceptance of these projects. Are there known factors that influence community support or resistance? Any insights or examples would be appreciated.
So I can jump in here and then let others comment, but so HEET is a nonprofit that is working to drive the thermal energy transition. And the concept that HEET is working on is really to bring utilities in, to work with utilities to adapt these thermal energy networks as part of their business model. And the reason for this is that the utilities can do this at scale. They have set up our entire gas system, right? And they have a funding mechanism that allows them to have this upfront capital cost and amortize it through, 30, 50 years throughout their rate payers. So there is a system through the utility model to really do it at scale so that communities don't have the burden of that upfront capital cost. Utilities are regulated, and traditionally they have only been allowed to sell gas to their customers, for example, gas utilities. So that regulation needs to change and is changing in different states. In Massachusetts, since this last year, now utilities are allowed to pursue these geothermal energy networks as part of their business model. So different states have been passing these changes. And that is a way to have these systems not only at scale, or bypass that large capital cost for the customer, and also do it in an equitable manner. And there was a question about that equity in and affordability. So just, yeah.
And I would also just add on the upfront CapEx cost for these projects. That really touches on the underlying motivation behind everything that Celsius is trying to do in this space, right? So, I mean, just looking at our work in using this small footprint inclined pyramid bore field design. I mean, we're reducing the amount of surface piping that a project needs typically by about 70%. We're reducing the total number of bores that actually need to be drilled by about 30%. On the Framingham project, just in that one parking lot alone, the surface footprint that we needed to do excavation work, trenching work, all of the associated site work that geothermal projects need in order to be executed, we were able to reduce that by 74%. So these are all ways that we can try to reduce that upfront capital cost on these projects. It's not specific to thermal energy network jobs. I mean, even just your, quote unquote, vanilla, straightforward, single building, single bore field geothermal project would benefit from that. But that's definitely a driving factor behind, everything that we're trying to do and achieve in the field right now.
Great. We are about out of time, so I just want to thank Isabel, Joshua, and Jay for their great presentations today, and thank all of our attendees for joining us. I hope everyone has a wonderful rest of their day and a great weekend. Bye, everyone.
Bye.
Thank you.
Thank
Bye.
you all.